Welcome to our short subject on understanding process capability. So we're going to take a look at a couple of process capability indices, the PCI and the CPK. We're going to take a look at the situation of continuous data from our process that's normally distributed, continuous data from a process that's not normally distributed, and then what if you have a process that just generates attribute or countable discrete data? We're going to take a look at that situation as well. So we're going to understand process capability, and what we're trying to do with process capability is compare the process variation that we have to the customer requirements, the customer specification. So that's typically defined as something of an upper and a lower specification limit, and then we're going to compare our distribution to it. So with the PCI, the process capability indice, we're going to take the total width of that specification, and we're going to compare it to our distribution, its total width, or 6 standard deviations, which would be approximately 99.97% of all the data. All right. The other indice that we have is a thing called the CPK. The CPK helps us to understand where is our distribution. Is our distribution centered in our specification, or is it toward one side or toward the other side? All right. If our distribution is perfectly centered, then the CPK and the PCI are going to be exactly the same value. But what's going on with the CPK is we're going to take a look at if our distribution has an average value here, how close is it to this specification or to this specification? Whichever closest specification we have, then we're going to take that distance, divide it by 3 standard deviations, or half of that distribution, and that'll give us the CPK. So if we were perfectly centered, this value and this value are going to turn out to be the same thing. All right. So we have a couple of situations here. We can get process capability if we can meet all of our assumptions, or we can just get current process performance. All right, so the assumptions that we have: our process exhibits statistical control as evidenced on a control chart. It's only common cause, normal natural patterns of variability. No special causes. All right? There's no weird things going on in our data set as it is tracked over time. All right? It's normally distributed, and we've got at least 50 data points. So if we can meet all of this criteria, then what we're going to perform is a process capability study. If we are not in statistical control, then that would be a current process performance study, which will give us an idea of where we are, but it's not the true capability because our process isn't stable yet. So we'd have to fix that. All right, so what we're going to do is we're going to compare product specifications to the natural variation of our process. All right, so what's that normal, natural, random pattern of variability that we have? And we can depict that with a histogram or taking a look at the distribution. So here's a couple of cases. Now what we've done is I've put the process capability indice, its values, on this side. I've put the CPK values on this side. All right. Now the process capability indice doesn't care where the distribution is located. And you can see that right here. Here's this distribution, and it's pretty small, it's pretty tight, big wide specification limits. Yes, we're very capable. We're a process capability indice something greater than 1.33. And 1.33 is a special number, and we'll talk about why that's important in a little bit. All right, so here's this distribution. If it's here, or like in this case, it's way over here, where some of its tail is outside of the upper spec, guess what? The PCI says, hey, you're perfectly capable. So the other measure we have, the CPK, says, whoa, hold on a second, you're not centered. All right, so if we're centered, PCI, CPK are the same. We begin to drift off center. Now one of the tails of our distribution, even though the spread would be perfectly capable, I have a tail that's outside of the spec. I have defects. All right, so my CPK is less than 1. In this situation, my distribution is the full width of the spec. All right, so it's 1 is less than the PCI, which is less than 1.33. Same thing with the CPK. Now, I'm in a situation where my distribution stretches beyond the spec limits. All right, both of these situations, the PCI and the CPK, have values that are less than 1, so we're not capable. All right, so this is not capable, not capable, not capable, capable. How about this situation? We're greater than 1.33, but we aren't past the spec, but we're getting real close to it. Well, that's the situation where the CPK now is going to be between, it's less than 1.33, but it's a little bit greater than 1. All right, so those are the different scenarios that we could have depending on how much variation there is in our process as we compare it to the customer requirements, the customer specifications. This is what our process generates. These are man-made. All right, so we see that our process is shifted over. We see that we have a CPK that is less than 1.33. So what does that mean? Well, we can figure out how much of our distribution is generating parts or products that are not conforming to the specification. So what's that percentage that's outside of the specification? Well, to take a look at that, we can use a thing called a z-statistic. All right? The z-statistic is based on the standard normal distribution, which has a mean of 0 and a standard deviation of 1. So the z-stats, if I want to calculate the z for the upper limit or the z for the lower limit, it's just the difference between that limit and the overall average divided by the standard deviation. And that gives us a z-statistic. All right, could be for the upper value or the lower value. And then we look that up in a z-table. And then what that does is it's going to give us a value that is the percent of this distribution that's outside of the specification. All right, and typically we're looking at either one side or the other side. All right, so how do we use this to tell us how we're performing? Why is 1.33 such a magic number? Well, if we take a look at the standard normal distribution, we have the z-statistics and the percentage that are out of spec. Now we can take a z-statistic and we can determine what the CPK is. Okay, the z-min value divided by 3 is CPK. And then where's that process sigma thing from Lean Six Sigma? Well, the z-min value plus 1.5 is the process sigma value. Now it's starting to make some sense here. All right, so we can actually get the z-value, the percent out of specification, we get the CPK, the process sigma, and our defects per million opportunities. All right, so if we're at a z-value of 0, 50% of our distribution is outside the specification. Our CPK is 0, our process sigma is 1.5, and we've got 500,000 defects per million opportunities. Now if I get down here to a z-statistic of 4, all right, that's a process sigma of 5.5, that's our magic 1.33 number. All right, so less than 0.003% of what we produce is going to be out of specification, or we're going to have a whopping 22 defects per million opportunities. Now, in Six Sigma, the definition of a process sigma level of 6 is 3.4 defects per million, and that translates into a z-statistic of 4.5, or 0.0003% of the distribution is going to be outside of the specification. All right, so this is a shortened version of a z-statistic table, and I just put some specific values in here so you can see the z-value, percent out of spec, CPK, what the process sigma looks like, and the defects per million opportunities. And these things are all tied together. All right, so now, what are you going to do if your distribution is not normally distributed? All right, you've done the control chart. It looks like it's stable over time. You've done a look at your data set and you're seeing it's not normally distributed. All right, so what we have to do is a Boxcox transformation so we can turn that data into normally distributed data. Now, typically using the Boxcox, What we want to stick with are lambda values, because the Boxcox transform is your individual data point y raised to the lambda. And so if we stick to some common lambda values of 2, okay, it's y squared. 0.5, square root of y. 0, natural log of y. All right, minus 0.5, 1 over the square root of y. Minus 1, 1 over y. So if we stick to these standard common transforms, it's very easy for us to undo what we did if we need to undo it. All right, and also it's easier to understand the transform that we just pulled off, and it's easier to calculate. Here's the kicker. If we're going to do this transform to our data, don't forget to transform your upper spec and your lower spec using the transform and the lambda that made your data normally distributed. So that these now are in the same format as your new transform data is. And then, using everything we just talked about, the CPK, the PCI calculations, the Z statistics, everything else, that's all going to work because now you have converted your data set into a normally distributed set of data. So you just use the Boxcox transformation, pick one of the common transforms. Don't forget to transform your specifications. All right, now, what if your data from your process is not continuous data, it's attribute data, it's count data, it's percent defective data, it's defects per unit data. All right, well, those are attributes, all right? So here's the rules. Once again, you gotta have 50 data points and our process has to exhibit statistical control as evidenced on a control chart. Then, and this is pretty straightforward now, all right, the P-chart. Is the P-chart stable over time? Only common cause variability? If it is, then your process capability is P-bar, the average fraction nonconforming. If you have a C-chart, if it's stable over time, your capability is the average count of defects. If it's stable over time using a U-chart, your average defects per unit is your capability. So it's pretty straightforward to do attributes and a capability study, 50 data points, make sure in statistical control, and then it's just the center line of any one of the attribute charts that you've used to prove that you are stable.